So, in this case, this one was a power plant down in Texas. It was the very first claim that I ever went on as a broker's engineer. And when I got to the site, I had never been to a claim before, but I met the adjuster and I met the plant manager, started going through some of the events, what happened, and the OEM team was there. And this was a 501G, $16 million compressor wreck. So it was a big deal. I had no idea, what I was going to face when it started. But we talked about, the circumstances before the event, what happened, and how they knew that they had a loss, and then what was done after the equipment was known to be wrecked, as far as investigating and figuring out what happened. So I recall that the adjuster went into another room, made some calls, and I started to pick up that it wasn't a real open, collaborative process. So he came back in and we did some talking, and we came back the next day. And he told me the next day that blades that were in the road that were not damaged would be salvaged, and that the scrap value of those blades would be used against the claim, and that it would be about $600,000. And I said, well, show me where it says that in the policy, because I didn't know where it was in the policy, and I had never looked at that policy. I'd looked at other policies and I understood insurance. He couldn't find it anywhere in the policy. So he was taken back, and he kind of realized that he couldn't just shoot from the hip. But he did shift gears and decided to call the damage high cycle fatigue, and that was wear and tear, and that damage, that those blades would not be covered. It was very interesting because I asked if the insurance were to pay for things that were predictable and known were going to happen, and we could put the brakes on, so to speak, and take a look at the condition of the equipment. And of course not. Insurance not going to pay for things that we can manage, but insurance is there for things that we really can't manage. Things like high cycle fatigue. You can't bring a turbine down every couple of hours to inspect it for high cycle fatigue, because that's how fast it occurs. It takes about 1 million cycles, and I'll tell you how they started to get the cycles. The way the 501G works is it's a huge compressor that sucks the air in, and one way to get more power out of it, you squeeze that air, you push it into the combustor section where you add the fuel. The expanding exhaust gases go right across the turbine blades. These are taking the hot gases on the front end. You're basically taking in outside air. It gets hot as it goes through the compressor because it's being compressed, and that adds the heat to it. So one thing you can do to improve power is to get more air, more mass of the air flowing through this machine. Kind of like a turbocharger would be on a car. Instead of just waiting for the engine to suck it in, you push it in. Well, the way that we can do it on a large scale is that we can bring in cooler air, and if we can cool the air, it'll be heavier. It'll have more oxygen in the same amount of volume. So now we've achieved that goal of shoving more oxygen through the machine, and we can get more power out of it. So how do we cool the air? Well, in this case, they can use evaporative coolers. And generally, the idea of the way these work, swamp cooler. Just think of, in Arizona, the way you cool some houses out there, swamp cooler. What this evap cooler was doing was basically taking water and running down the media, and the water would evaporate. The cooler water would cool down the air. That would achieve the goal of augmenting power. The evap cooler media was basically cellulose material, And when the water supply was changed from normal raw water to demineralized water, the demineralized water attacked the binders in the cellulose in the media of the evap cooler. So then that media would slowly dissolve and go downstream and eventually get collected on the inlet of the compressor. So that first stage blades had this glob of filter media just starting to build up on the intake. And if you can imagine a row of turbine blades going around, and there's one little section where there's this glob of media blocking the suction. Just think about all the blades going around. And if you looked at the side of the blade, as the blades passed that area where there was the obstruction of airflow, they wouldn't be doing any work and they would unflex. Well, then they would flex again as they got past it. So you would have this constant state of every blade going past that area of blockage of the air supply, and it would flex. So you had this 3,600 RPM flexing of this piece of metal, and eventually it failed. Okay, so that was high cycle fatigue. The metallurgy confirmed that. The problem was the wrong water being used. It was poor design. And the OEM stated that the water that was used was too clean and that they were going to change their standards to limit how clean the water could be. So in other words, that they were going to add in dirty water to the demineralized water. They actually used the term they wanted to have dirty demin. And that was going to solve the problem. What ultimately will solve the problem is to get away from cellulose evap cooler media and go to a fiberglass evap cooler media that's less susceptible to being dissolved by even the demin water. There was a special set of circumstances with this case because the adjuster really didn't understand the underwriting, and he mistook what would be normally salvage value. Most policies have that if you wreck your car, whatever residual value there was in it, if it's a total, that becomes the insurance company's property to dispose of as they wish. But in this case, there was a long-term service agreement. And when there's a long-term service agreement, what happens is the client or the operator of the power plant gets preferred pricing and preferred availability. So they get bumped first in line. If they have a forced outage, they get to get their parts as fast as possible. So they pay for that service every year. And as part of that service, they get this guaranteed cost of low price parts. And that's especially helpful when there's a wreck or an emergency, a need to get back up and running quickly. All of a sudden, then the price of parts usually goes up really fast. So locking it in before you have that need for them is a prudent thing to do. And the underwriters reward that. The underwriters understand what an LTSA is, and they take it into account when they underwrite these policies. And they give credit to the fact that the parts will be at a guaranteed lower cost, and that you'll have guaranteed advice on maintaining the plant. The adjuster was basically trying to double dip because he wanted to get the benefit of that, the lower risk, but then again take the piece of metal and go sell it. Where in that long-term service agreement, this thing that protected both the insurance company and the client, in that agreement was a requirement to return all broken parts to the manufacturer. I mean, that's what they wanted them back. They didn't want them just being scattered and distributed out and reverse engineered by anybody who got a hold of them. They had that in their contract. They wanted them back. So there was no residual value. That all the value in those blades was within the long-term service agreement. This adjuster, he didn't understand that and really wouldn't understand that discussion. So I had a discussion with the manager of the claims department at the lead underwriters company, and he completely understood. When I walked him through it, it was plain and simple that they understood what the benefit of an LTSA was. They've already got the benefit out of it. Nobody's double dipping. The LTSA says the blades go back to the manufacturer. So $600,000 of dispute between me and the adjuster got resolved in that discussion. And then he said, but the initial blade that broke, that one was from high cycle fatigue. We're not going to pay for that blade. And he wanted to argue over $20,000, which was kind of funny that he said that was the cost. But I asked the client, do you guys want to argue over $20,000 over this? And they said, you've gotten a $16 million. You don't need to fight over the $20,000. Thanks.